What are you doing, Roshan?
Doing the EM assignment, as you can see. Yeah, there's a problem that's bothering me. So you see, in nature there's 4 fundamental forces, right?
Yeah.
There's the gravity, strong force, weak force, and then lastly, of course, the electromagnetic force. But have you ever wondered why is it called electromagnetic force?
No, but why?
I mean, electromagnetic force suggests that they are the same force.
Yeah.
But then, even with your Maxwell equation, you see that B field and E field are 2 different fields. How are they even related?
I don't know. Let's just ask Professor Michael.
The new professor in SPMS?
Yeah.
Well, let's hope he's a nice guy. Let's go.
Hey. Hello, come in.
Good evening, Dr. Michael.
Hey, hi. Hi, how may I help you?
Physics problem to consult you on.
Okay.
Yeah, so it's about electromagnetism.
Yeah, so how are electrical field and magnetic field actually related, apart from,
The name
Maxwell
being
equation?
Maxwell equation. Oh, I see. You want to learn more about the fundamentals behind why the name is even called
As in why, how are they related? Yes.
Okay. Okay, come sit down. I'll teach you about it. Yes. Joseph, you can just stand there.
Yes, yeah.
Okay.
Thank
So
you.
the key idea behind this is called relativity.
Oh,
Yes.
what? Is that possible?
You'll be surprised. Okay, come. So today I'll teach you all about how relativity causes electromagnetism to happen. Okay?
Okay, cool.
Okay, come, gather.
Yes.
Okay, so today we'll be talking about how relativity relates electricity to magnetism. Alright, so first of all, assume that there's a wire infinitely long in length. So above the wire there's positive charges, and below the wire there's negative charges. So usually when I pass through a current through it, the negative charges will flow along the wire and reach there. So now suppose that I have a cation that is positively charged. As I pass through the current, during day-to-day life, we know that there will be nothing happening to the charge, as the wire is still electrically neutral, as the number of positive charges cancel out that of the negative charges. Now, what if the positive cation is now here, and it is moving at a certain velocity, which is equivalent to that of the velocity of the electrons. So when the entire system is moving, the cation moves along with the electrons. If we were to change the perspective of this motion, suppose that this is now moving and we change it to the rest frame, so it appears that the entire wire is moving away from the positive charge like this. Now, under such situations, because the top is now moving and the bottom is now stationary, what happens is that there will be length contraction happening, as predicted in special relativity. What this means is that when an object is traveling with a velocity v, from a point of view of an observer, this object will contract. Suppose its initial length is L, and its new length will then be L. And these two are related by the formula L equals to L naught over gamma, where gamma is the Lorentz factor, as given by such. So far so good. So what happens when the top layer, which is the positive charges, actually contract? So we already know that this is an infinite wire. So even when we contract it, the length is still infinite. The main point, however, is that the distribution of positive charges will now be squashed. So now the wire will look something like this. Right, so initially the wire has uniform positive charge above and uniform negative charge below. So once I consider the positive charges to be moving and the negative charges to be stationary, the positive charges will be squashed together as shown, and so on and so forth, whereas the negative charges will be more spaced out compared to the positive charges because the positive charges went through length contraction. Because of this, the general charge density will be rho. This is a positive number. Because of this charge, from the charge point of view, the entire wire appears to be like a positive charge. And when you put two positive charges next to each other, they will just repel each other. This is what we usually expect when we set a charge moving beside a wire, which is what we know as magnetic force. However, as you can see here, this is simply just relativity applied to electric fields. So that is why electricity and magnetisms are related via special relativity.
Thank you, Dr. Michael.
Hey, no problem, no problem.
That was a very enlightening for everybody.
Hey, you're welcome, you're welcome. Did you understand?
Yes, of course.
Are you sure?
I think so, yes.
Okay,
yes.
okay, that's very good. Alright, is there anything else you want to ask?
Is today dressed up Friday?
Yes, how did you know?
Huh?
Yes, I'm going dance later. Yes,
I
yes.
see, I see.
Anything else, Joseph? No. Okay.
Okay,
Sounds good.
thank you for your time.
Alright, no
I'll
problem.
visit you more often.
Yes, yes.
Oh,
See you again. Don't kick me.
Bye bye. See you.